Hello everyone, my name is Vageesha Sindhu from BSc Chemistry Honours second year. We are doing inorganic chemistry topic, that is chemistry of lanthanide elements. We have learned that elements in which last electron enters the f orbital of their atoms are called f block elements. In these elements, the last electron is added to the third to the outermost, called anti-penultimate energy level, that is n-2f. These elements are called inner transition elements because these constitute transition series within transition series d block elements. They consist of two series of elements placed at the bottom of periodic table. These two series are formed by filling of electrons in 4f and 5f orbitals and are called lanthanides and actinides respectively. The series involving the filling of 4f orbitals following lanthanum is called lanthanide series. The elements present in the series are called lanthanides. There are 14 elements in this series starting with cerium and ending with lutetium. The name lanthanide is derived from lanthanum, the first member of the series. These lanthanides are also sometimes referred to as lanthanons. All these elements have closely similar properties and therefore are considered together. The reason for their similar properties is that the 4f orbitals in which the electrons are embedded in the inner shells, while 5d and 6s electrons which have similar configuration are exposed more to the surroundings. Because of their similar physical properties, their separation and identification proved to be very difficult task. The first stage of their separation was to get them as oxides. However, the occurrence of the oxides of lanthanides was very rare. Therefore, these elements have also been called rare earth elements. Nowadays, the term rare earths is not used. The substantial deposits occur in Scandinavia, USA, USSR, and India. General characteristics of lanthanides. The important general characteristics of lanthanides are discussed below. Electronic structure and position in the periodic table. The lanthanides involve the gradual filling of 4f orbitals. It may be noted that energies of d orbitals and the next inner shell f orbitals, that is f4f, are closely similar and therefore the order of filling the 4f orbitals in the atom shows quite irregularities. At lanthanum, both 5d and 4f orbitals become stable due to the increased effective nuclear charge as a result of the poor shielding effect of 6s electrons. Therefore, it is observed that at lanthanum the incoming electron enters the 5d orbital and its electronic configuration is lanthanum atomic number 57, xenon 5d1 6s2. However, as we move further after lanthanum, the energy of 4f subshell becomes lower than the 5d subshell and therefore the next electron in cerium enters the 4f subshell. The filling of 4f orbital continues till we reach ytterbium, in which the 4f subshell gets completely filled. Now, after 6s and 4f subshell have been filled, the next electron goes to 5d subshell. The configuration of lutetium is xenon 4f14 5d1 6s2. Physical properties. The important physical constants of lanthanides are given. Ionization energies. The lanthanides have fairly low ionization energies. In general, the first and second ionization energies of the lanthanides increase with increase in atomic number, but the variation is small and irregular. The variation of ionization energies with atomic number is as shown in the figure. It is clear from the figure that some deviations are observed in the regular increasing order, such as for europium and gadolinium. These are attributed to the stability of half-filled and completely filled F subshell. The first ionization energy are of the order of 560 kJ per mole and second ionization energy are of the order of 1150 kJ per mole. These values are quite comparable to alkaline earth metals, especially calcium. Melting and boiling point. Lanthanides have fairly high melting and boiling point. However, the melting and boiling points do not show any regular trend as we move from lanthanum to lutetium in the series. Inspection of the table shows that europium and ytterbium have unexpectedly low melting and boiling points. These atoms form europium 2 positive and ytterbium 2 positive ions and result in weaker metallic bonding because there are less than 3 electrons per atom in the metallic bond. The other lanthanide atoms gives 3 electrons per atom in the metallic bond. Therefore, melting and boiling points of europium and ytterbium are as low as compared to the values of the other lanthanide elements. Density. The densities of the lanthanides are low, which range between 6.7 to 9.74 gram per centimeter cube. However, there is no definite trend in the density values of lanthanides with increase in atomic number. Europium and ytterbium have unexpected low values. Heat of fusion and heat of vaporization. The heat of fusion and heat of vaporization also do not show definite trends with increase in atomic number. Electronegativity values. The electronegativity values of lanthanides are quite close to those alkali and alkaline earth metals. Therefore, lanthanides are expected to form ionic compounds. Electropositive character. Because of low ionization energy and electronegativity values, the lanthanides are electropositive like S block elements. Oxidation states. The common oxidation states of all the lanthanides is +3. In addition, some lanthanides show +2 and +4 oxidation states also. These are shown by those elements which by doing so attain the stable F0, F7 and F14 configuration. For example, cerium and terbium exhibit +4 oxidation states. Cerium and terbium attain F0 and F7 configuration respectively when they get +4 oxidation states. Europium and ytterbium +2 oxidation states. Europium and ytterbium get F7 and F14 configuration in +2 oxidation states as shown. Exceptional examples. Some other elements show +4 and +4 oxidation states even though they have electronic configuration other than F0, F7 or F14. For example, samarium and terbium show +2 states having F6 and F13 electrons respectively, in which they have one electron less than half filled or completely filled configuration. Similarly, praseodymium, neodymium and dysprosium show +4 oxidation states having F1, F2 and F8 electronic configuration. The stability of these unusual oxidation states may be dependent upon some other thermodynamic and kinetic factors which are of significant importance, but these are less stable than the +3 state which is characteristic of this family. Color and spectral properties. The lanthanides are silvery white, but many lanthanide ions are colored both in the solid state and in the aqueous solution. The colors remain same even on the change of anions. Therefore, the colors are characteristic of the lanthanide ions. The color of the ions depends upon the number of unpaired electrons because it has been observed that the ions containing NF electrons have almost similar color to those with 14 minus NF electrons. The different ions having NF and 14 minus NF and their colors are given in the table. However, it has been observed that some di and tetra positive ions having same number of electrons as tri positive ions do not have same color. For example, samarium 2 positive and europium 3 positive have same number of unpaired electron but they have different colors. The color of the lanthanide ions arise due to the absorption of light from visible region of the spectrum resulting in the electronic transition within 4F level. A remarkable characteristic of the spectra of tri-positive lanthanide ions is that the absorption bands are extremely sharp line-like bands in ultraviolet, visible or near infrared regions. Many of these bands are line-like and become even narrower as the temperature is lowered. This behavior is in contrast to absorption bands of DD transitions, which have broad absorption band. The bands of lanthanide ions are so sharp that they are useful for characterizing the lanthanide ions. The main reason for very sharp absorption band is that 4f orbitals lie deep in the atom of these elements. Therefore, they are effectively shielded from the surroundings by overlying 5s and 5p orbitals, and consequently the absorption band arises mainly from the electronic transition within 4f levels. Thus, the absorption band show little dependence on the nature of ligand. In addition to FF transition, sometimes color of lanthanide ions is also attributed to FT transition. The FF transition sometimes color of the lanthanide ions is also attributed to FT transition. The FF absorption transition of lanthanide ions have low intensity because they are not allowed, whereas FT transition are allowed. In contrast to FF transition, the FT transition are allowed and hence show very intensive absorption band. For example, the FT transitions observed for cerium 3 positive and terbium 3 positive are very intense. Magnetic properties. All the lanthanide ions with the exception of La3 positive, Lu3 positive, Ce4 positive and Yb2 positive ions are paramagnetic because they contain unpaired electron in their 4f subshell. The ions lanthanum 3 positive, lutetium 3 positive, cerium 4 positive and ytterbium 2 positive, which have 4f0 and 4f14 electronic configuration, are diamagnetic because they have no unpaired electron. The magnetic properties of the lanthanides are different from those of transition elements. As we know, the magnetic moments arise from two types of motion of the electrons. The spin motion of electron around its own axis produces magnetic moment called spin magnetic moment, while the orbital motion of electron around the nucleus produces magnetic moment called orbital magnetic moment. The observed magnetic moment of a substance is due to the contribution of both the spin moment and the orbital moment. In the case of transition elements, the magnetic moment mainly corresponds to the spin-only magnetic moment. This is due to the fact that the d orbitals are not well shielded from the environment and take part in bond formation with the ligands. As a result, the d electrons of the metal interact strongly with the ligands surrounding the metal ion. Due to the electric field of the ligands, the orbital motion of the electron gets restricted and thereby the orbital moment of these electrons get quenched. The magnetic moment of d block elements thus arises mainly from the contribution of spin motion of electron only. The spin only magnetic moment is given as mu spin only is equal to under root n into n plus 2, where n is the number of unpaired electron. This relationship gives almost correct values of the magnetic moment for d block elements. However, the above relationship is not valid in the case of f block elements. In these elements, the 4f orbitals are well shielded from the surroundings by the overlying 5s and 5p subshells. As a result, the electric field of the ligand surrounding the metal ion doesn't restrict the orbital motion of the electrons. The orbital contribution is not quenched, therefore the magnetic moments of lanthanide ions is due to both electron spin and orbital motion of the electrons. This can be calculated from the relation mu is equal to under root 4s into s plus 1 plus L into L plus 1, where S is the resultant spin quantum number and L is the resultant orbital momentum quantum number. The theoretically and experimentally observed magnetic moment values are given in the table. The magnetic moments of lanthanides depend upon the atomic number and the number of unpaired electrons. For the ions lanthanum 3 positive, gadolinium 3 positive and lutetium 3 positive, the magnetic moments corresponds to spin only values. For these configurations, there is no orbital angular momentum, that is L is equal to 0, and the magnetic moment may be calculated only on the basis of spin only value. The magnetic moments of tri-positive lanthanide ion are plotted in the graph. It is observed that the value increases up to neodymium and then decreases. For samarium 3 positive ions, it increases again and reaching a maximum value for dysprosium and holmium. Thereafter it starts decreasing and becomes 0 for lutetium, which is diamagnetic. The unusual shape of the curve arises because when the F subshell is less than half full, the spin and orbital magnetic moment work in opposite, but when the F subshell is more than half full, they work together. Ionic radii, lanthanide contraction. We know that as we move down a group, atomic size normally increase. This is mainly due to the additional shell of electrons between the successive periods. However, as we move across a period from left to right, atomic sizes decreases. This is attributed to the increasing effective nuclear charge, as a result of which the outermost shell of electrons is attracted more and more. Consequently, the size decreases. If we consider the ionic radii of lanthanides, we get very interesting observation. For comparison's sake, we can take the ionic radii of trivalent ions M3 positive, which are most stable. These are shown in the figure. It is clear that ionic radii decreases from one element to another in the lanthanide series, but decreases very small. It has been observed that from cerium 3 positive to lutetium 3 positive, the ionic radii decreases from 1.03 angstrom to 0.86 angstrom. Obviously, for an increase of atomic number 14, the decrease in ionic radii is only 0.17 angstrom. This is very small decrease in comparison to elements of other group and periods. Similarly, on moving from cerium to lutetium, the atomic radii also decreases from 1.65 angstrom to 1.56 angstrom, and the decrease is only 0.09 angstrom. This small steady decrease in ionic or atomic sizes of lanthanide elements with increase in atomic number is called lanthanide contraction. Cause of lanthanide contraction. In lanthanide series, the 4f electrons are being added one at each step as we move from one element to another. The shielding of one f electron by another from the nuclear attraction is quite weak due to the shape of the 4f orbital. The nuclear charge, however, increases by 1 at each step. Hence, with increasing atomic number and nuclear charge, the effective nuclear charge experienced by each 4f electron increases. Hence, the inward pull experienced by the 4f electron increases, and this causes a reduction in the size of the atom or ion. The sum of the successive reductions give the total lanthanide contraction. Consequence of lanthanide contraction. Lanthanide contraction has very significant effect on the relative properties of the elements which precede and which follow the lanthanides in the periodic table. Some important consequences of lanthanide contraction are given. Steady decrease in size. There is a regular decrease in the ionic radii of lanthanides. Electronegativity. There is a slight regular increase in the electronegativity of the trivalent ions. Electrode potential values. There is a small but smooth increase in standard electrode potential values for the process. Resemblance of second and third transition series. The lanthanide contraction affects the chemistry of second and third transition series. As we can see from the table, there is a regular increase in size from scandium to yttrium to lanthanum. Similarly, we expect normal increase in size in other groups as from zirconium to hafnium and from niobium to tantalum. However, after lanthanides, the increase in radii from second to third transition series almost vanishes. The pair of elements zirconium, hafnium, niobium, tantalum, molybdenum, tungsten, etc. possesses almost the same size. The properties of these elements are also very similar. As a result of lanthanide contraction, the elements of second and third transition series resemble each other much more than the elements of first and second transition series. Similarly, among lanthanides, because of very small change in the size of the lanthanide ions in lanthanide, their chemical properties are similar. Therefore, their separation become very difficult. Recently, methods based on repeated fractional crystallization or ion exchange techniques which take the advantage of slight differences in their properties arising from very slight size differences of their trivalent ions have been used. Basicity differences. Due to lanthanide contraction, the size of the lanthanide ions decreases regularly with increase in atomic number. As a result of decrease in size, their covalent character between lanthanum 3 positive ions and OH negative ions increases, and therefore the basic strength of the hydroxides decreases with increase in atomic number. Thus, lanthanum OH thrice is the most basic, while lutetium trihydroxide is the least basic. The basicity differences in lanthanides are reflected in increasing tendency to get hydrolyzed. Due to decrease in basic character, there is slight increase in degree of hydrolysis in solution from lanthanum 3 positive to lutetium 3 positive. The thermal decomposition of oxysalts. More basic oxysalts decompose less rapidly. Solubility of salts. Lanthanide hydroxide precipitate at regularly decreasing pH values from lanthanum 3 positive to lutetium 3 positive at 6.83 and 6.30 respectively. Sizes of ytterbium, holmium and dysprosium. Due to lanthanide contraction, the radii of ytterbium 3 positive is comparable to heavier lanthanides, that is terbium, dysprosium, holmium and erbium. Therefore, they occur together in natural minerals. Reactivity of lanthanides. All the lanthanides are highly electropositive metals and have almost similar chemical reactivity. This is due to the fact that the lanthanides differ only in the number of 4f electrons. Since these electrons are very effectively shielded from the interaction with other elements by the overlying 5s, 5p and 6s electrons, they show very little differences in their chemical reactivity. Because of their similar chemical reactivities, their separation from one another is very difficult. The lanthanides are in general more reactive than D block elements. Some of their chemical characteristics are they tarnish readily on exposure to air. In finely divided state, all burn in air to form ciscosides of the formula Ln2O3 except cerium which gives CeO2. Ytterbium however resists the action of air even at 1000 degrees Celsius due to the formation of a protective coating of its oxide. All react with water slowly in cold but rapidly on heating, liberating hydrogen and forming LNOH thrice. All these combine with hydrogen at 200 to 300 degrees Celsius giving LNH3. They also combine with halogens, oxygen and sulfur. They act as strong reducing agent for oxides of other metals. Cerium is used as a scavenger of oxygen and sulfur in many metals. They react with nitrogen to form nitrides of the formula LNN. Solubility of compounds. The fluorides, oxides, hydroxide, carbonates, phosphates, chromates and oxalates of lanthanides are largely insoluble in water. On the other hand, the halides other than fluorides, nitrates, acetates, perchlorates and salt of oxoacids of lanthanides are soluble in water. The solubility behavior of salt of lanthanides follows the pattern of solubility of salts of group 2 elements. However, lanthanide sulfates, unlike the sulfates of group 2 elements, are soluble in water. Tendency to form complexes. Although the lanthanide ions have a high charge, yet they have large size of their ions. As a result, they have low charge density and therefore they have very less tendency to form complexes. Their complexes with unidentate ligands are very few and form complexes only with fluorine and oxygen donor ligands. However, they form complexes with a few chelating ligands such as beta diketones, oximes, and ethylene diamine tetraacetic acid, alpha alpha dash dipyridyl, and hydroxyl carboxylic acids such as citric acid. These complexes usually have high and variable coordination number, and water or solvent molecules are often attached to the central metal atom. Beta diketone complexes of europium 3 positive and praseodymium 3 positive dissolved in organic solvent are used as lanthanide shift reagents in NMR spectroscopy. In contrast to transition elements, the coordination number 6 is not very common. Coordination number below 6 is also uncommon and occurs only with bulky ligands such as 2,6-dimethyl phenyl ligands. However, coordination number 7, 8 and 9 are common, and these give a variety of stereochemistries. Ce4 positive is smaller and highly charged and form CeNO3 6 2 negative in the non-aqueous solvent N2O4. This is 12 coordinated cerium in which each NO3 negative ion uses 2 oxygen atom to coordinate to the metal. When two transnitrates of this complex are replaced by triphenyl PH3PO, it gives the 10 coordinated orange colored neutral complex. The sulfates cerium sulfate NH2O and NH4 twice CeSO4 twice are the iodates are also known. Large number of salts of organic acids such as oxalic acid, citric and tartaric have been studied mainly for separation methods. These anions have chelating oxygen ligand forming complexes with Ln3 positive. Unidentate oxygen donors such as pyridine N oxide and triphenylphosphine oxide also form many complexes with lanthanides in +3 oxidation states. Complexes with ligands such as En, di-En, bipyridyl and terpy can also be prepared in polar organic solvents. As with other transition metals, the lanthanides can be induced to form complexes with exceptionally low coordination number by use of bulky ligands such as NSI Me3 thrice negative. This is an example of coordination number 3, which is the lowest form for lanthanides. They are volatile, air sensitive and easily hydrolyzed. They are planar in solution but pyramidal in the solid state. Lanthanides also form two main types of organometallic compounds, predominantly ionic cyclopentadienides and sigma bonded alkyls and aryls. These type of compounds are usually thermally stable but unstable with respect to water and air. The series Ln C5H5 thrice and Ln C5H5 twice Cl are salt containing C5H5 negative anion and are readily prepared by the reaction of anhydrous NaCl3 and NaC5H5 in appropriate molar ratio in THF. In polar solvent, these complexes are solvated and are monomeric, but in non-polar solvent, the tris C5H5 compounds are insoluble while the bis C5H5 compounds dimerize. The lanthanides also form alkyl and aryls by metathesis in THF or ether solution. Triphenyl are polymeric in which Ln is tetrahedrally coordinated to form 4 sigma aryl groups. Methyl derivatives have also been obtained. Octahedral Ln Me6 three negative species of lanthanides have been isolated. In contrast to transition elements, the lanthanides do not form complexes with pi bonding ligands such as CO, NO, CNR, etc. The difference arises because the 4f orbitals are well shielded and are inside the atoms. Therefore, they can't take part in pi bonding, whereas in the transition elements, the orbitals are commonly involved in pi bonding. Double salt formation. The lanthanide salts form double salts with corresponding salts of ammonium and alkali metals. Double salts like alums with 24 water molecules are not formed. This is because the lanthanide ions are so large that these can't coordinate to 24 water molecules octahedrally as in alums. Thank you.